As I mentioned last week, I think I did, or 2 weeks ago when we had the actual theory, we will switch a little bit the topic. Still robots, but we'll talk about different type of robots today and next week. Today we'll talk about drones. Yes, you've heard about them. So we will see a few things about the principles. In order to understand how drones work, we need to understand a little bit about aerodynamics, which is a topic I really like and I wanted to include in this lecture. But just the basics. And that's basically so we understand how propellers work, so that we can understand how drones are designed, how they are flying, and therefore how can we design the dynamic model and how can we control them. Okay? So far we've seen I think 100% we talked about this kind of robots. And as I said, the next two lectures we will talk about this lecture about drones, and next lecture will be about mobile robots. Again, how we describe them, how we control them. Okay. Now, when I say drones, what comes in your head? What do you know about drones? How do they look? What types do you know? Okay. Or videos at weddings and stuff. Yeah. And they are what? A what? Eh? A weapon maker. Ah, a waffle maker. Yes. Sometimes, yes. Okay. They're used, for making pictures or videos only. What other use do you know for drones? Races, yeah. Yeah, that's entertainment, let's say. Right? What other types? On this. Have you ever heard of Amazon trying to use drones? They're not used yet, but how could Amazon use drones? Delivery, yeah. They are claiming they want to do it for almost a decade, I think. They haven't managed yet. Okay, so maybe delivery. Okay, that's much faster than going by road, you go by air. Remote surveillance, again, like camera, video, and so on. Agriculture, yeah, for surveying crops and or spraying pesticides or things like this, yes. Okay, and another type that is very popular as well is for entertainment, again for light formations and for, I don't know, have you ever seen shows like this? There are drones flying in a swarm and then different lights appearing and then you see things on the sky based on their formations. So it's very, very interesting. Disney is working this. Okay, so one type of drones that we'll see today, we may well discuss, is this. Yeah, you could say the waffle maker. Depends. Yeah, there are some of them have protective things around that makes it look like a waffle maker. Yeah, it's this quad rotor drones or quadcopter. Okay, why do they call it like this? Four, quad from Latin, I guess. Four. Yeah. Why four rotors? Why is this so popular design? Why not three? Why not five? Stable? Okay. With three, it would be stable too, no? With two, not. Okay. Okay, for aspects of what's the fourth one? So what is this pitch roll yaw? And this, the height. Okay. Okay. Nice. So we can only rotate them and put them up, down, remove them. Anyway, how do we call them in robotics? These aspects, degrees of freedom. Very good. So This kind of links to what we saw in articulated robots. We had 4 joints. We could have had maximum 4 degrees of freedom. The 3 joints we have 3 degrees of freedom, right? Here again we have 4 motors and we get 4 degrees of freedom. We'll see how and why not more and so on. Okay? And we'll see if these 4 degrees of freedom are enough or not, and so on and so forth. Before we start understanding degrees of freedom and so on, I want to mention some things about aerodynamics. What is your relationship with the subject? Any idea about aerodynamics? You know what it is about aerodynamics? What does the word tell you? Aero means air in Greek. And dynamics. So, moving in the air, or not necessarily in the air. If we do it more general, it's how objects behave in the dynamic way when they are moving in relation to a fluid. It can be air. Usually it's air. Aerodynamics about air. Okay, yeah, you have hydrodynamics, which is moving in water, or you can have fluid dynamics, which is for any fluid. But yeah, aerodynamics is usually about air. And what's your relation? Have you ever had any discussion either in high school or in, I don't know, at the university about aerodynamics? Nothing? Okay, what would you think it has to do? Okay, it has to do with moving in a fluid, but what aspects? When we say, okay, a car is very aerodynamic, what do you understand? Have you ever heard of this before? Why? The air resistance. So it has to do with air resistance, with how easy it is to move on a fluid. Okay, so basically, one very important and relevant thing of aerodynamics is this concept of, resistance. That has to do, let's say, with cars. Okay, but another aspect, more related to airplanes, for instance, how they fly, it's a thing that is called the lift. Okay, the resistance is how we usually call it as drag. How much is dragging us back in a way, okay? You can think of this as resistance, and you have a lift. The lift is the force, the same as the resistance is a force. Lift is the force that raises the airplane in the sky, okay? And these two forces, we'll see they're very relevant for the drone modeling and so on. Now, how do these forces get generated? How does the airplane get this force that lifts it from the ground? By moving forwards? More specifically, let's say, what is it moving forward? Let's say I have the airplane moving relative to what forward? To the ground? To the air? To whatever? To what? What is the thing that generates the lift? To the air, right? So it doesn't matter how fast the airplane is moving relative to the ground, for instance. What generates the lift is the relative speed between the wing of the airplane and the air. Okay? Because the airplane can be sitting like still. If there is wind blowing, there will be some lift generated on the wings. I don't know, maybe you've seen like birds. Sometimes, if it's a strong wind, they stay like this and they hover. Have you ever seen birds like this? That's because there is relative speed between their wings and the air, because the wing is blowing. Or they need to put a bit of effort just to stay there. Okay? So there are like these two forces that play a role, and they generated by the relative speed of the wing of the airplane and the fluid that they're in, the air, let's say. Okay? And another force that is very important is the weight. Okay, and basically these three forces, they generate, and there is also the thrust. The thrust is the thing that is pushing the airplane in front. Okay, what is that in an airplane? The engines. Right? They generate the thrust. Okay, so we have these four forces, and the total sum, if we add them all together, these vectors will point hopefully somewhere upwards and maybe a bit backwards. Okay, or no, sorry, maybe a bit front, so that the thing actually moves front. Okay, good. Now, how can we affect these forces? The weight we cannot affect, right? Because the weight is fixed of the airplane. How can we affect the thrust? The thrust, we said, is the power, the force that is produced by the engine, right? How can we affect that? Higher engine speed by pushing the pedal down, okay? And how can we affect the lift and the drag? What do you think? Any ideas? The angle. Okay, what do you see here? It's called the angle of attack. Okay, it's the angle of the wing relative to the flow of the air. Okay, and what else? And the design of the airfoil as well, of the wing. Of course, different wing designs have different parameters of how this lift and drag work. If I have a flat thing, it produces no lift. So if it's a bit curved, that's why wings are a bit curved, it produces different lift based on the design and so on. Okay? Yes? Yeah, I think that's more things into that play a role there. I think there is a lot of drag in that case. Now, why you say that when you go in the sea, it's easier to go in, but it's more difficult to come out? I think there it has more like waves that play into, because they're into roll and some currents and stuff. But yeah, I don't know. Because basically, why am I saying this? How do you get this lift? You need to have like quite a big speed, right? The airplane needs to get, I don't know how many kilometers per hour in order to start having an effect and having a lift. And also, the relative speed has to be quite high to start getting aerodynamic effects and so on. Okay. The idea is basically the thing that we directly control. Let's say the design of the wing we cannot change while the plane is flying. We make it, we build it, and it's fixed. Although you've seen they have these flaps things that extend during takeoff and landing. Have you seen the wing shape changing a bit sometimes? Well, this is why they do it, so that they affect a bit how this relationship is, how the lift and the drag are working. Okay, so we can change the shape of the wing as well during flight, but the main thing that we can change is the angle of attack. Okay, and this angle of attack, basically for the same wing type, it generates different lift and drag based on what is the angle relative to the airflow of the wing. Okay. Here you can see the bit schematically that I can have a very low and very low lift and drag when the wing is kind of like flat. When I put it in a higher angle of attack, I get more lift and the drag does not increase so much. But if I keep on doing this, I get a lot of drag while not producing enough lift. Okay, so there is like a sweet spot where it gives me a good ratio of lift and drag, because I want to keep the drag low. That's resistance. So if I have low drag, I have less fuel consumption. So, okay. Now, why is this related to drones? Basically, a propeller looks like this. I guess you've seen propellers from drones or from I don't know, airplanes and so on. Okay, and as you see, so what you see here you see the propeller from the front, and here you see cross sections of the propeller. Okay, so it's as if I cut the propeller here, I will see something like this, something like this, something like this. Okay, and each one of these is like a small wing. Okay, this thing is rotating, let's say in one direction. And what happens by rotating the propeller? What do I create? I create relative motion between the propeller and the air, right? And we saw that this thing creates lift and drag. Okay? The higher the speed, the higher the relative velocity between the propeller and the air, the higher the lift and the drag. Okay? But we see that these cross sections, they represent the wing, but the form of the wing is different. And if you see a propeller, it's kind of like a twisted thing, right? As you see it here. Now, why is it so that basically what are we changing here? We're changing the shape of the wing, or the airfoil as we call it, but we also change, as you see, the angle of attack, right? The elements here at the side have a smaller angle of attack than the elements here towards the center. And we saw that smaller angle of attack gives me lower lift, okay, or lower force. Why do you think it's that? Why do I want to have a smaller angle of attack here, no, a bigger angle of attack here and a smaller here? So I want it to be thicker, you mean, or what? Why do you want it to be more resistant in the center? The force is it? Now, you said many things. You said in the center we have bigger lift. Why is that? Yes, but we saw that the lift is also related to. Do you see it? What is it? What else is it the lift related? What did we say that we need in order to have lift? We need speed, right? So here we have a bigger angle of attack, so yeah, the lift would be bigger, but what about the speed? Is the speed here and here the same? Why not? Yeah, if I have the same angular velocity all over the wing, all over the propeller, the elements in the center, they move slower than the elements around outside, okay? Therefore, in order to have like a more or less equal force produced along the wing here, okay, I need to change this angle of attack. So I have a smaller angle of attack here because I have a bigger speed than what I have here. Relative speed with the wing and the air, right? So that's why propellers have this twisted shape that you see here, kind of. Okay? Of course, it's also the thing you say here, it's not just the angle of attack that's different, it's also like more solid, because here you have, if you have a force produced here, it creates a moment that tries to bend the propeller and other kind of stuff. So yeah, in the center it has to be stiffer. But the idea with the angle of attack is so that we have like an equal force produced here along the propeller, and we achieve that by having different angles of attack because the resulting speed will be different along the. Okay. I just find it, when I discovered this, I found it really cool, and I thought of mentioning it here too. Now, a drone has 4 of these, right? A quadcopter. There are drones with more as well, but let's stick to 4. So a drone has 4 of these. So let's start putting these propellers on the drone and trying to make like a system of reference for describing the drone. First, we'll talk about kinematics, I'll describe the kinematics and then about velocities, and eventually we're going to see the dynamic. So a drone looks more or less like this, where we have the four motors. Each motor has a propeller on it, and yeah, we kind of attached a coordinate frame along an axis of the drone. Usually we put it in the center of the drone, okay? And we have a fixed reference frame here, okay? So the idea is that we want to describe the position and orientation of this coordinate frame relative to this coordinate frame. That's what we always be doing in with articulate robots, and that's the same idea. You can see this as the end effector of the robot, right? Because that's what we want to control eventually. Now, by having propellers here, what do we produce? And how is this drone flying? By rotating this propeller here, what is the effect? What do we get? A what? A lift, okay, a force, okay, from, let's say, the center of the rotation pointing upwards, okay, and only that. Do I get something else? Rotation around the x-axis. So x is the red. Okay, so I'm not talking, let's say, generic. Just remove the motor and have the propeller there. By rotating this, let's not talk about the drone yet. Just what happens at each individual propeller. So Mario said we have a lift because this thing rotates. It produces a force upwards. Let's say, depends how it's rotating, of course. Do I get something else? What happens with the drag? So the lift produces the force upwards. What happens with this force? The drag here. What do I get if I have my propeller, let's say, rotates? I will get the force pointing outwards. Okay. Because, wait a bit, because I have some force here, 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 here. So the sum of all these forces will be pointing towards you, let's say. And just let's stick to this propeller only for now, okay? So here I will have like some lift. Let's show it on the side as well. Let's say this rotates around here. I will have lift and then the sum of all these forces will be like a force pointing upwards. Okay, so this is from the side, this is from the top. What about the drag? I will have some drag here. Okay, if it's rotating like this, and here. What will this give me? This will be equal to this, right? So the force will be equal to 0. But what else do I get? A what? No. A thing called torque. Will I get some torque? Because from here I have this force times this distance. Okay? This force times this distance, this force times this distance, and so on. I will get the resulting torque from these forces, and here I will have a torque pointing in the opposite direction. Okay? But torque does not cancel. I mean, these two torques, they will not cancel each other out. They will produce a bigger torque. because they both point in the same direction, in the same rotation, right? So from here I will get the torque like this, and from here I will get the torque like this, so the sum will be a torque twice as big, right? Related to this, you know why helicopters have propeller up and a propeller on the side. Right, propeller like this produce some torque, which if you don't counterbalance somehow, they will rotate the whole helicopter together with the propeller. Okay. So if you want to shoot down a helicopter, aim for the propeller in the back. However, the idea is that I get here a lift force in each one of them, but I also get the torque, which, if the propeller is rotating like this, the torque will be in the opposite direction. Okay? Now, this is something we use, and now this is aerodynamics that we're not going to discuss about, but the idea is that this force and this torque that I get is proportional to how fast the propeller is rotating, squared, to the square of the angular velocity of the propeller. Okay? B and D are some constants that have to do with the design of the propeller and so on. And it's not the purpose to see how we calculate them. Okay? Good. We'll see how we use this force and torque. Now, let's define some notation. We will call XYZ translation of the origin of the drone frame relative to the fixed frame along the XYZ axis. Okay, and phi, theta, and psi, rotation around the XYZ axis of the fixed frame. Okay, and if we put these two together, we call this, we will use this notation for today. These three together, the linear translation, we'll call it xi, the vector of translation, and the vector of rotations, we call it eta. Remind you a bit of Greek. And both together is s. So these will be the coordinates that we talk about today. See eta. Now, if I do the if I try to write the transformation matrix from the fixed frame to the frame of the drone, I will get something like this. Okay, so this is the transformation matrix for these angles theta, psi, and phi, which I will write here because we will need it later on, from fixed frame A to frame of the robot, where I have, this is just the rotation part, okay, theta, psi, psi, s theta, s phi, minus c phi, s psi, I'm running out of space, s phi, s psi, plus c phi, c psi, s theta, c theta, c psi, c phi, c psi, s theta, s phi, s psi, c phi, s theta, s psi, minus c psi, s phi. How did I get this? How would I get this? I multiply the transformations by taking a rotation around x, around y, around z with phi, theta, psi. Okay? If I take these three rotations, I multiply them together, I get this thing. Okay? Now, c theta, c psi means, c theta means cosinus of theta and sinus of psi. I just write it condensed. Okay? Don't have to know this by heart, but we will use it a bit later on. That's why I wrote it down. Okay. Now there are two ways that we are controlling drones, and we'll see how can we manipulate the position and orientation of the drone based on these two configurations. First is the X configuration, and the other is the plus configuration. Why X? Because it's like an X. Why plus? Because it's like a plus. Okay? Basically, it has to do with how we position X and Y relative to the robot. Okay? And let's see how we control the position of the robot, let's say in this X configuration. Z, by the way, it's pointing towards you or towards the board. X, Y, Z. So towards you. No. In the board. X, Y, Z. Okay? So in the board. Good. So what do I need to do? Just think intuitively. What do I need to do? How should I control? What should be the? No, one step back. Sorry. What is the thing I'm controlling in this drone? Is it the speed of each motor? Right? Great. Now this is the difference with articulated robot, with a robotic arm. There we were controlling mainly, we could control the speed of the joints, but we were mainly controlling the position of the joints. Here the position of the joints would be a bit silly, because by changing the position I'm not changing the force generated, so I fly. I need to have constant speed, right? So let's say I want to change the Z position of the robot. What should the relationship of the speeds of the motors here be, so that I just change the Z position. So I move it up and down. They have to be
changed with the same amount.
Okay, they have to be equal, right? Great. And then by increasing all of them or decreasing all of them, I'll get the different lift, because we saw that lift has to do with velocity. Okay. And the idea is that if I keep all of them the same, by changing the amount of omega, I change the position. Okay? Good. How could I do so that I rotate around the x-axis?
Change only half of it.
Change only half of it. Which half?
The ones on the right.
The ones from the right, the same amount, and the ones from the left, the same amount. And by changing their ratio, I change this orientation. Okay, I produce more lift on this side than on this side, so I change the orientation, right? So I keep omega 1 and omega 3 the same, and omega 2 and omega 4 the same, and I change the ratio of the two. Right? The same for, or similar for Y. I keep omega 1 and omega 2 the same, and omega 3 and omega 4 the same. Right? So this is three aspects or 3 degrees of freedom I can control. What would be the fourth one? Because we said at the beginning that we have 4 degrees of freedom. Around Z. Okay. Why not translation on X, for instance? Could I change independently? Now, what did we say degree of freedom is when I change one coordinate independently from the others, meaning I change, let's say, translation of Z without changing orientation or translation in the other directions. So, how could I change, for instance, translation on X?
We have to change the rotation on right. We change the pitch, and then
so we tilt the robot, and that will result in, because the overall can be divided into two forces. Why is that? Let's see the robot. Let's say I change on Y. So I close the robot here. Close, whatever. So this is Z, and X involved. Okay? So this is just seeing the robot from below. How would I make it go on Y? I will need to tilt it. Okay. Here I'm exaggerating. Okay, and that will make it go towards there, towards Y. Why? Basically, in this situation, I have the force generated here pointing upwards, and I have the weight here pointing downwards. And if the weight is double of this 2, then I will have also no torque in this table. Okay, but in this case, where is the lift pointing towards? The lift is pointing towards there, right? And where is the weight pointing? The weight is still pointing downwards. Okay, so this balance of forces will give me a resulting force pointing there. Oh, sorry, depends how I do it. It hopefully will point towards there. Just there. Based on how big are these relative to these. I can make it point there or a bit higher. If it points high, it will also fly. Okay? But the idea is that I cannot change the Y position without changing the rotation around X. So this is not independent changing of the two coordinates. Right? Similarly, I cannot change rotation around X without changing Y position. Because the moment I kill the robot, it will start going to the right. Okay? Good. So that's how you can understand why we only have 4 degrees of freedom with 4 motors on the drone. Now, you said that another thing, so this is with the 2 translations, which I'll show you later. The 2 translations, I achieve them by doing rotation around the 2 axes. How can I do rotation around Z?
Changing the speed diagonally.
How?
Omega 1 and omega 4.
Omega 1 and omega 4?
Need to change with the same amount.
Why do you say that?
Because
It's a good answer, but why? Just because of the combinations, or?
no, because in that case the torque won't be equalized and it will rotate.
Okay, so basically omega 1 gives me a torque like this, if it rotates like this. Omega 4 gives me a torque like this as well. So the total torque will be like this, the sum of the 2 torques. Okay, and omega 3 gives me a torque in the other direction, and omega 2 also in the other direction. Okay, so this will give me a torque like this. Okay, so if I use these things wisely, I can change the amount of torque generated from omega 1 and omega 4 and make it smaller or bigger than the one produced by this omega 3 and omega 2. Okay, so that I have a resulting torque that will make my robot rotate around, my drone rotate around Z. Okay, is it clear? Can you understand? So basically that's how drones manage to rotate around Z as well. And this is the 4 degrees of, or you could say, some of the 4 degrees of freedom. Because we would say I have translation on X and translation on Y. Okay? The idea is that translation and rotation, translation on X and rotation on Y, they are coupled. I cannot change them independently, and the same for translation on Y and rotation on X. Okay? Now, yes?
Can you explain again the rotation around the X, because I just don't
The rotation around Z or
around X.
the rotation around X.
So omega 1 and omega 3 are equal, but in our case, the control is like, let's say like this, and these are the
So if this is equal,
Yes.
first of all, the torques will be cancelling each other out.
Yes.
Okay, that's why we want them equal. And they will produce some force. Let's say we see the robot as I do it here. Okay? And this is Y. This is Z. So X pointing X. Okay, and this is omega 1, omega 3. And this is omega 2, omega 4. Right? So we want these two equal so that the torque cancels each other out. So I don't have a rotation. Okay? And it produces some force. Okay? And we want omega 2 and omega 4 equal, so again they cancel each other, the torque out. But let's say I rotate them less fast than omega 1 and omega 3. Okay, so they produce a smaller force. So let's call this F1, F2. Okay? And what other force do I have here? I have weight. Okay? Now this thing, if I choose F1 and F2 to be equal, the sum of them to be equal to W, will give me a zero force here, right? Let's say F1 plus F2 is equal to W. So the sum of the forces will be zero. So this will not move up and down. Okay? But I have torque as well. How do I calculate the torque here? Let's say this is torque around this. Okay, what would be the torque? What is torque? What is the function of the? How do I calculate torque? Is force times distance. Right? Force times distance is torque. So I have F1 times this distance. Okay, and let's call it L over 2. And this is also L over 2. Okay, I'm looking for the torque around this center. So F1 L over 2. What is torque 2? F2 times L over 2, but this produces a negative torque. Right? So minus F2 L over 2. Okay? And the weight? 0. Why? Distance 0. Okay? Good. So the sum of torques will be F1 L over 2 minus F2 L over 2. Okay? So if F1 and F2 are not equal, if they're equal, F1 and F2 are equal, what do I get here? 0. Right? If they're not equal, I get the resulting torque, positive or negative. Okay? That will make this thing rotate. It will not move up and down because the sum of the forces is 0, but the sum of torques is not 0. I thought you had, you were more familiar with torques, but I guess not so much. I should have started with that. Okay? Torque is force times distance. That's why here I get the torque. Yeah?
And I want to rotate random axis. And at the beginning I need higher speed, and then I have to equalize the speeds to remain on the same
Yes. Why? Let's take the example, not the rotation. First, let's take the example that I want to change height. Okay? Let's say I just want to move in the Z direction. What did we say we want to do? If I don't want to rotate, the torques have to be 0. Okay, but this has to be positive. So I move up. Okay, so I increase F1 and F2. The moment this happens, I will get a sum of forces not equal to 0. Let's say sum of forces equal to, I don't know, 5. Whatever. That means 5 meters. What will be the result of this? What is the sum of forces equal to? From Newton?
Mass times all the
mass times acceleration. Okay? So I will start accelerating on Z. Okay? And if I keep on this force there, I will keep on accelerating. So I will start accelerating. If I want to stop, what should happen? I should put this to 0. Okay? So I change the speed so that I produce some force. The sum of these forces minus the weight has to be positive, so it starts moving up, or negative if I put Z down, whatever, doesn't matter. Okay, but if I would stop, I have to equalize this back to B0, which means that the forces has to be equal to the weight. That will give me 0 acceleration. Will it give me 0 speed? No. Yeah? Very good. So if I just do this, I will stop accelerating, but I will keep on moving with a constant speed. Not exactly, because I will have some aerodynamic resistance as well, so I will slowly slow down. But if I want to control the position, then I have to put this for some time to negative, so I also, I need to do like more complicated stuff. You understand what I'm saying, right? Because if I just put this 0, the acceleration will be 0, but the speed will remain the same.
Sorry.
Thank you for waiting us up. Any more questions here? How these things work? Okay, the idea is that by playing with the relationship of these 4 motors in a smart way, I can control positions and orientations and stuff like this. Okay? You said about drone racing, when people are doing drone racing, that's what they're thinking. They think more intuitively, but basically the controller of the robot, of the drone, they have controllers, and when you say push, go forward, it knows, it has some control inside that it, changes the relationship proportional to how much you're pushing it. Now, let's see about the quad plus configuration. It's basically the same thing, slightly different. Translation of Z means equal rotations here, and by changing the amount, the velocities are moving up and down. A rotation on X now means basically omega 1 and omega 2, omega 3 have to be equal, and then these two have to be unequal. Okay? You understand? This has to be unequal. It's the same, similar logic. And the same one on Y. Rotation around Z means exactly the same thing. Okay? Rotation on X means translation on Y, and translation on X means rotation on Y. Okay? One small detail that I forgot to mention, but I kind of mentioned there, is that you notice that these 4 motors, they don't all rotate in the same direction. Okay, you see 2 rotate counterclockwise and 2 rotate clockwise. The same thing here. If they would all rotate in the same direction, I would have a resulting torque always in the same direction to the controller. It's the helicopter that takes that. Okay? Shall we take a break? Or do you have more questions before the break? So this is, let's say, the kinematic modeling. How am I changing position and rotation by changing the speeds of the motors. So afterwards we will see the dynamic